In this supplementary video, we will solve all the leftover problems in exercise 4, so that on Thursday, we can start exercise 5 and do not need to worry about these problems anymore. Okay, let me start from problem 4. So you were given a function g, whose graph is depicted like this, and you need to find the limit at the infinity and limit at the negative infinity, limit at 0, the left-hand limit at the number 2, the right-hand limit at the number 2, and finally, you need to find the equation of asymptotes. So here by asymptotes, I mean both the vertical asymptote and the horizontal asymptote. All right, so let's first investigate the infinite limit over here. So this means you need to let x get positively large. And as a result, you see that the function value, although it's actually oscillating, but it's still going to be getting close to this line over here. And this line has got the y coordinate 2. So that's how I can conclude that my limit of g of x as x gets positively large, it's simply going to be equals to 2. Okay, so this solves the part A. Okay, let's look at part B. So you're asked to find the limit of g of x as x gets negatively large. So let x goes negatively large and see where the function value is approaching. And you can see that the function value is approaching this line, and you'll read from the graph that this is precisely y equals to -1. So that way I conclude that the limit of g of x at minus infinity is simply -1. All right, so this solves part B. Okay, for part C, we are asked to find the limit of g of x as x approaches 0. So if x is approaching 0 from the left, you could see that the function value shoots down to negative infinity. So the left-hand limit at the point 0 is going to be -infinity. On the other hand, if you look at the right-hand limit, so x gets close to 0 from the right, well, the function value also blows down to -infinity over here. So this basically tells me that the two-sided limit, namely the limit of g of x as x approaches 0 from either side, well, this is going to be -infinity. So that way I can conclude part C. Okay, for part D, so if x is approaching 2 from the left, you see that the graph is shooting down to -infinity. So that way you see that the left-hand limit at the point 2 is -infinity. On the other hand, if x is approaching 2 from the right, you see that the function shoots up to positive infinity. So that's how I conclude that the right-hand limit at the number 2 is positive infinity. So because these two guys are not the same, so the only thing we can say about the limit of g of x as x approaches 2, so the only thing we can say about this guy is it does not exist. So notice that, well, theoretically speaking, you could also say that for part C, D, and E, you can simply say the limit does not exist, but that's not precise enough. So the precise solution will just be what we have done over here, because, well, the limit being positive or negative infinity are precisely special ways for the limit to be not existing. And in chapter 4, when we deal with the graph sketching, you will find this information useful. All right, so that concludes the discussion of part A through part E. Finally, we need to find the equation of the asymptotes. We will start from the horizontal asymptote. And as you could see from here, well, limit at the infinity equals to 2. So this will tell me that y equals to 2 is a horizontal asymptote. On the other hand, the limit at -infinity equals to -1. So that would tell me that y equals to -1 will also be a horizontal asymptote. So that will be the answer for the horizontal asymptote. So this function has got 2 horizontal asymptotes. So for the vertical asymptote, all you need to figure out is where the function gets negatively or positively large. So as you could see that when x gets close to 0 or when x gets close to 2, well, one of the limits is going to be infinity. So that's why I can say that the vertical asymptotes are simply x equals to 0 and x equals to 2. All right, so this concludes the problem 4. Okay, so problem 8 is a little bit tricky because this is really an open-ended question. So you are only asked to sketch the graph of an example of a function f satisfying all these conditions. So the solution to such kind of open-ended problem is not necessarily unique. So first, let me draw xy coordinate and mark all the necessary knowledge over here. So first, because the limit at positive infinity equals to 3, so I know in particular the y equals to 3 is going to be horizontal asymptote. So the function can approach 3 in this way or in this way, so at the far end. So that's what I can know from the first restriction. On the other hand, the function approaches in positive infinity as x approaches 2 from the left. So this means as x approaches 2 from the left, my function is going to shoot up to positive infinity. On the other hand, if my x is approaching 2 from the right, then it's required that the limit is negative infinity. So that means the function should look like this. Okay, so so I think the behavior at the number 2 is quite clear, but then over 3, it could be either this way or this way over here. There's ambiguity. And well, whenever ambiguity happens and you're only asked for an example, just randomly pick one and that should be fine. So let me actually just pick this one because that one is the easiest to draw. So let me just leave these marks on my graph like this. So I'm looking for a function whose graph near x equals 2 looks like this, and whose graph as x gets large looks like this. Okay, so finally, there is a requirement that f is an odd function. So odd function simply means the graph is symmetric about the origin. But before you finish the graph anywhere else, you need to keep in mind that for an odd function, it is necessary for you to have f of 0 equals to 0. And why is this the case? So this is because, well, by the definition of the odd function, f of minus x equals to negative of f of x. And if you plug in x equals to 0, so you will get f of 0 equals to minus f of 0. So if you move the right-hand side to the left-hand side, you see that 2f of 0 equals to 0. And as a result, f of 0 has to take 0. Okay, so now let's see what we have. So we have got a function whose behavior near 2 looks like this, whose far end behavior like this, and who is passing through 0. And certainly there are many different ways for you to achieve the same. For example, your function can be look like this, and the function can look like this. Or if you decided that your graph is going to be approaching 3 from above as x gets large, so then you might have got a graph looking like this. And moreover, you might have another graph looking like this. So there might be all kinds of different cases that you might have. So these are all possible solutions to this problem. So this is how this problem is kind of open-ended. But the simplest possible solution you might expect is basically the following, where you will simply connect these bits directly by smooth curves so as to get this part and this part. All right, so this is what the graph looks like when x is positive. Now, to obtain the other half, namely to obtain what's going on here, all you need to do is to rotate everything by 180 degrees so as to get something. So this rotated by 180 degrees basically looks like this. Okay, so this will be one possible solution to this problem. And certainly if you decided your graph looks like this and looks like this, then when you're trying to do the symmetry, well, it will actually look like this, and then it will look like this. Yeah, so it's really depending on what you choose on the right-hand side over here. Regarding the intersection of asymptote, I should give 2 remarks. So the first remark is, well, the graph can intersect the horizontal asymptote without any trouble. So you could actually have got a graph looking like this, or have got a graph that looking like this. It can intersect the horizontal asymptote many times. It really doesn't cause any troubles. On the other hand, well, near the vertical asymptote, you are not allowed to have got some function behavior like this. So indeed, if the curve intersects the vertical asymptote for more than once, well, then the curve fails to be the graph of a function, because in this case, the vertical line test will fail. So, so to summarize, well, the curve can intersect the horizontal asymptote many times as you want, but the curve can intersect the vertical asymptote for at most once. Well, some possible example is simply like this. So I can simply supplement a solid dot over here. So this is also considered an intersection. Of course, you might have some other cases. So for example, if we do not have this requirement that the right-hand limit is minus infinity, then a possible configuration of this function is going to be like f of 2 takes this value, and then it will approach 3 as x approaches positive infinity. So that's the case where you may have got a function intersecting the vertical asymptote for once, but please make sure that only one point on the graph is sitting on the vertical asymptote. Okay, so this is what I want to say about the problem 8. And now let's look into the next problem, problem 50. So you are asked to find the horizontal and vertical asymptotes of each curve. If you have a graphing device, track your work by graphing the curve and estimating the asymptotes. Okay, so this is number 50. So we are given the curve y equals to 1 plus x to the 4th on top and x squared minus x to the 4th at the bottom. Okay, let's start with the vertical asymptotes. So in order to find the vertical asymptotes, we need to find out where the denominator takes 0. So you can see that the denominator can be factorized in this way. So I can factor out an x squared. So what remains is going to be 1 minus x squared over here. And this 1 minus x squared can be further factored as x, 1 minus x, 1 plus x. So the denominator will simply be this guy, and we set it equals to 0. We see there is 3 points, x equals to 0, 1, and minus 1. So these are the 3 numbers making the denominator 0. Okay, but in order to make sure we have got a vertical asymptote, please definitely make sure you track also the numerator, and please make sure the numerator is non-zero. So when x takes these numbers, well, the numerator 1 plus x to the 4th will respectively take these 3 numbers. So if you plug in x equals to 0, you get 1. If you plug in x equals to 1 or x equals minus 2, you will get 2 and 2. So all these numbers are non-zero. Okay, so because you have got non-zero numerators, you can safely say that x equals to 0, x equals 1, and x equals to minus 1. These guys are indeed vertical asymptotes. So the remark I should provide is that only when the numerator is non-zero and the denominator equals to 0, only in this case could you conclude a vertical asymptote. So in particular, this means if your numerator happens to be 0, and then you will actually have got something like a 0 over 0 type. And in this case, well, this kind of limit is indefinite, and you cannot conclude a vertical asymptote in this case. Well, before continuing with the horizontal asymptote, let's actually look at a very similar example that's not in the textbook. So I will change the plus in the numerator into a minus. So in this case, if you focus only on the denominator, you will still find 3 numbers, x equals to 0, 1, and minus 1. But if you look at the numerator over here, so if you see that when x equals to 0, so the numerator is going to be 1, which is non-zero. So this way you can safely say that x equals to 0 is a vertical asymptote. However, when x equals to plus minus 1, so the numerator 1 minus x to the 4th, this guy equals to 0. So in this case, you have got 0 over 0. So this basically means you need to investigate the limit of this fraction at number 1 and the limit of this fraction at the number minus 1. Okay, so the computation is very simple, so I will not go over the detail, but directly show you the result. So because we know that when x is not plus or minus 1, so we can factorize the numerator and the denominator into this form. So the numerator is going to be factorized as the product of 1 minus x, 1 plus x, and 1 plus x squared. And the denominator is factored into the product x squared times 1 minus x times 1 plus x. Okay, so you see that there are many common factors, and then you could get rid of these common factors. So what remains is going to be 1 plus x squared divided by x squared. So this equality is valid when x is not plus or minus 1. In particular, it's valid when x gets close to 1 and negative 1. So that's why we can conclude that the limit of my original fraction is simply going to be 1 plus 1 divided by 1, and this is going to be equals to 2, and this is not going to be plus or minus infinity. And similarly, the limit at the negative 1 is also going to be equals to 2, and this is not plus or minus infinity. So our conclusion for this problem is, well, only x equals to 0 is a vertical asymptote. Okay, I hope that the previous example emphasizes my point that only when the numerator is non-zero and the denominator is equals to 0 could you conclude a vertical asymptote. Okay. The horizontal asymptote is considerably easier, so I will just go over the solution very quickly. So all you need to do is to look at the limit at infinity and the limit at minus infinity. So you just compute it using the drills we introduced in class, dividing both on top and the bottom by the highest power of the denominator, which happens to be x to the 4th. So after the division, you get something like this. And now you can simply say that this guy goes to 0 and this guy goes to 0 to conclude the limit to be -1. And similarly, you could do the same computation over here. I will skip the process. And you also get -1 as the limit. All right, so this way you can conclude that y equals to -1 is the only horizontal asymptote. Okay, I'm not going to do the graphing in this video. You can play with that by yourself, and you simply play with the decimals. And then, but please make sure you zoom out and zoom in the graph appropriately. So otherwise, you might not be able to see the vertical asymptotes appropriately. So for example, this is a graph you can make by making the unit for the y-axis to be large. So from this graph, it will be clear that you will have got 3 vertical asymptotes at these 2 points. And roughly speaking, these are going to be -1 and 1. On the other hand, the horizontal asymptote is not very obvious because you see that because we made the units for the y coordinate to be very large. So the -1 over here will be very, very close to the x-axis. But if you zoom out a little bit, and you will see that y equals to -1 is really a horizontal asymptote. Okay, so please play with decimals by yourself. And the point for this requirement is to convey the idea that, yeah, even though you have very advanced graphical calculators, it's necessary for you to do such kind of analysis because the initial graph you are getting from the decimals might be very misleading and you might not be able to observe these vertical asymptotes. And when you observe these vertical asymptotes, you might not be able to observe this horizontal asymptotes. So yeah, definitely try that yourself and to get some experience about that. Okay, so this is a discussion for number 50. For the modified problem, number 50 prime, so when I change the positive sign into the negative sign, you could also do the horizontal asymptote relatively easily. So all you need to do is to compute these limits. Well, you actually get the limits to be 1 as well. So then the conclusion for that problem is, well, only x equals to 0 is a vertical asymptote and y equals to 1 will be the horizontal asymptote. I will leave it to you to play with the decimals by yourself. Okay, let me do the next one by hand because the computation is slightly trickier and involves logarithmics. So we need to do the same for the curve y equals to 2 times e to the x divided by e to the x minus 5. So the drill is the same. You basically start by looking at where the denominator equals to 0. So you see that the denominator, in this case, is going to be e to the x minus 5. And if you want to set it equals to 0, you will see that e to the x has to be equals to 5. And you should recall from Eddie Wu's video that e to the x equals to 5 means x equals to natural log of 5. All right, so x equals to natural log of 5 is basically the number making the denominator 0. But remember, you need to also check the numerator at this point. So when x equals to natural log of 5, you see that the numerator is going to be e to the natural log of 5. Okay, e to the natural log of anything, that will simply be that thing by itself. So e to the natural log of 5 is simply going to be 5. And in particular, I see that this guy is non-zero. So we check that the numerator equals to a non-zero number while the denominator equals to 0 at the number x equals to natural log of 5. So our conclusion is x equals to natural log of 5 is the only vertical asymptote. Now to study the horizontal asymptotes, we need to investigate the limit of this fraction as x approaches infinity. So one thing you should keep in mind for this problem is, so just recall, so as x gets large, so e to the x also gets large. This tells me that my fraction 2e to the x divided by e to the x minus 5. So this is of the type infinity over infinity because both the numerator and the denominator gets large. So infinity over infinity type limit is really an indefinite type of limit. So then you need to use algebra to transform it into a definite type. And in order to do that, remember what we did for rational functions and algebraic functions, we divide by the highest power of x in the denominator. In this case, well, it's very natural for me to divide e to the x. Okay, so what I will do is to divide by e to the x both on top and at bottom. All right, so what do I get? So I will get x approaches infinity of, well, on top divided by ex, what I get is actually 2. At the bottom, if I divide everything by e to the x power, what I will get is 1 minus 5 over e to the x. All right, so then what do we do the next? So the next thing you need to do is to recall the following. So we know that e to the x gets large, so then 5 over e to the x will then be something like 5 over infinity in code. Well, 5 over a very large number, that will give me a very small positive number. So this is actually going to be equals to 0. And moreover, I can actually tell that this guy is approaching 0 from above, because 5 over e to the x is always positive. So it's approaching 0, then it has to be approached 0 from above. So this information is not used in this problem, but it might be important in the later part of this course. Okay, so because 5 over e to the x is approaching 0, so then we know that 1 minus 5 over e to the x, so this will have got a limit to be 1. So the denominator has got a limit 1, and we are allowed to use the algebraic laws regarding the quotients to conclude that our limit over here is going to be 2 divided by 1, and the answer will be 2. All right, so this is the limit at positive infinity. On the other hand, let's look at the limit at minus infinity. So this is much simpler, because again, you need to recall, as x approaches minus infinity, what will e to the x approach? Well, e to the x will approach 0. Well, you would also know that it's going to be approaching 0 from above. Okay, so because e to the x is approaching 0 from above, so I can see that the denominator e to the x minus 5. So this guy is approaching 0 minus 5, and this is going to be minus 5. In particular, it's non-zero. So it's precisely because of this, we could use the algebraic laws for the quotients to conclude my limit to be 2 times 0 divided by 0 minus 5. And the answer for this will be 0. Okay, so the conclusion for this problem is, well, y equals to 2 and y equals to 0 are the horizontal asymptotes. So if you ask Desmos to draw the graph for you, so you actually see that Desmos will give you something like this. So you could see that, well, the function is actually going to look like this. And in particular, there will be a horizontal asymptote as x approaches positive infinity. And the horizontal asymptote, you can read the number from Desmos, it will be 2. And as x gets negatively large, so you see that the x-axis is another horizontal asymptote, so as we see from here. So you could also see that there is actually a vertical asymptote at this point, although, yeah, Desmos will probably give you a number, but it's very hard for you to recognize that it's precisely natural log of 5. I'm not familiar with the natural log of 5 myself on this problem. All right, so that's what the graphing device can generate for you for this problem. Okay, so these are the three problems regarding the horizontal and vertical asymptotes. So please make sure when you're trying to find the vertical asymptotes, please make sure you check the numerator to be non-zero. We will conclude this supplementary video by the following 3 problems using the squeeze theorem. So notice that the squeeze theorem in this case is just the version at infinity. I never covered this part in the pre-lecture videos, and nor does the textbook mentions it, but then it appears in the exercises. So that's why I still need to actually say something about this squeeze theorem. Let me just write down the version of the squeeze theorem for limits at infinity. So the statement of the theorem is as follows. So if you have got a function f of x that is bounded below by g of x, and that is bounded above by h of x, and if you know that the lower bound function has the limit at infinity being the same as the upper bound function as x approaches infinity. So these two functions will have the same limit as x approaches infinity. Then the squeeze theorem basically says the middle function, namely f of x, will be forced to have the same limit as well. So this is basically the version for the squeeze theorem at infinity. So the statement is basically the same, except that the limit is now taken at positive infinity. Well, if you replace the limit to be taken at negative infinity, then similar result hold. So similar results holds for the limit at minus infinity. All right, so this is the version of the limit at infinity for the squeeze theorem. All right, so let's look into problem A1. So we are trying to find the limit of sine of x divided by x as x gets large. So the idea for this problem is basically the same as all the previous problems involving the sine and cosine function. So you make use of the upper bound and lower bound of sine of x. So sine of x is always bounded between -1 and 1. Moreover, since we are looking at the limit as x approaches positive infinity, so in this case, we know that x is positive. So then if I divide the first inequality by x everywhere, so the inequality does not need to change the directions. So what I will get is precisely -1 over x, smaller equals to sine x over x, and smaller equals to 1 over x. So then this will be my lower bound function, and this will be my upper bound function. All right, so as x approaches positive infinity, we see that -1 over x approaches 0, as well as 1 over x. So 1 over x is also approaching 0. So then squeeze theorem will tell me that the intermediate function sine of x divided by x. So this is forced to have 0 as the limit. So you see that the drill is completely the same as you have seen in exercise 2. Okay, let's look into the next problem, namely limit of e to the x times cosine x. Oh, there is a typo in the problem set, and as I announced earlier today, so it should really be e to the positive x, not e to the minus x right here. Okay, so if we look at the limit of e to the x times cosine of x, so the drill is basically the same. You first handle the trig function by a similar estimate. Then you multiply both sides by the e to the x to find the upper bound and lower bound function. Well, let me just do it very quickly here. So starting from the estimate, -1 is less or equals to cosine of x is less or equals to 1. And moreover, notice that e to the x is greater than 0. If I multiply e to the x to this inequality, then, well, these inequality signs do not change the directions. All right, so that's what I will get. I will get minus e to the x to be smaller or equals to e to the x cosine of x, and then smaller equals to positive e to the x. All right, so minus e to the x will be the lower bound function for this guy we are interested in, and positive e to the x will be the upper bound function. And notice that we are looking at the limit at negative infinity. So you should know that as x approaches minus infinity, so the upper bound function approaches 0, and the lower bound function minus e to the x also approaches 0. So then the squeeze theorem implies that the limit of the middle function is now forced to be 0. So this is another example of the limit at negative infinity. Finally, for A3, you are given a function defined on 0 to infinity, and moreover, you are given an inequality like this. So you're now asked to find the limit of f of x as x gets large. So, well, because in this case, the lower bound and the upper bound function are explicitly given, all you need to do is to compute the limit of this lower bound and upper bound function and investigate if they're the same. And, well, they are always all the same. Otherwise, you will not be able to compute the limit of f of x. Okay, let's see what we have. So as x approaches positive infinity, so we see for the lower bound function e to the minus x. So when x gets very large, minus x gets negatively large. So minus x is approaching minus infinity. So then e to the minus x will approach 0 because e to the very negatively large number is going to be very close to 0. So that's why I can say that e to the minus x approaches 0, so that e to the minus x plus 2 approaches 2. On the other hand, for the upper bound function, so we have got 2x squared divided by x squared minus 1. If you simply plug in a very large number x, you will see that this is infinity divided by infinity. So this is indefinite type of limit, and you need to divide everything by the highest power of the denominator, which is x squared. So then I can divide everything by x squared so as to get q divided by 1 over 1 minus x squared. And you see that 1 over x squared approaches 0. So this fraction approaches 2 divided by 1 minus 0, and the answer will be equals to 2. So you see that the lower bound function approaches 2 and upper bound function approaches 2. So squeeze theorem directly applies, implying that my limit of the function in between as x approaches positive infinity, so this guy is going to be equal to 2, and that will conclude this problem.